when it's over, that's the time I fall in love again.
Now that we've given the definition of a maximal ideal, and we understand the maximal ideals in Z, we're going to prove a proposition that's going to give a really useful way to test whether an ideal in a commutative ring is maximal or not. So let's assume that R is a commutative ring with identity 1 not equal to 0. So remember, in section 7.4 of Dummett and Foote, R is always a ring with identity 1 not equal to 0, and here we also need it to be commutative. An ideal M of R is maximal if and only if the quotient of R by M is a field. And how is the proof going to go? In one sentence, the idea is that we know a lot about the ideals in fields. This is something that we proved at the beginning of this lecture. And we also know a lot about how ideals in R relate to ideals in R mod M. All right, so let's turn this into a real proof. We're going to apply the lattice isomorphism theorem for rings. Let's say M is an ideal of R. It says that there's an inclusion preserving bijection between ideals J of R containing M and ideals J mod M of R mod M. Now, we'll just write down the definition of what it means for M to be a maximal ideal and translate it over to what it says in this quotient R mod M. So M is a maximal ideal if and only if there are no ideals J of R such that J contains M and J is not equal to the whole ring R. But now when we apply this bijection, if you have an ideal that contains M of R, you get a corresponding ideal of R mod M. So there are no ideals J of R satisfying J sits in between M and R if and only if there are no proper non-trivial ideals of R mod M. Right? I mean, think about what happens. If J is equal to M, you get the trivial ideal of R mod M. If J is equal to R, you get the entire ring R mod M. And if you have a non-trivial ideal, a proper non-trivial ideal of R mod M, then you exactly get something in the middle here. All right, so M is a maximal ideal if and only if there are no proper non-trivial ideals of R mod M. But what is a commutative ring with identity that has no proper non-trivial ideals? That's exactly a field by this part 2 of proposition 9 that we proved at the beginning of this lecture. So we have seen that you can tell whether or not an ideal is maximal by taking a quotient and seeing whether you get a field. OK, so I'll pause and erase, and we'll look at some examples of ideals and determine whether or not they are maximal ideals using this proposition. Let's now give 2 quick examples to show how to apply this proposition to check whether or not an ideal is a maximal ideal. Let's first consider the ideal generated by 2 and x in Z bracket x. This is a maximal ideal. Why? Well, we saw in each of the last 2 lectures that Z bracket x modulo this ideal is isomorphic to Z mod 2Z. We first did this by identifying this ideal as the kernel of a ring homomorphism. And then we also did this by using the second isomorphism theorem for rings and the third isomorphism theorem for rings together. But the point is, Z mod 2Z is a field. So this ideal that we quotiented by must be a maximal ideal. All right, and let's pick another ideal in the same ring. The ideal generated by x is not a maximal ideal. How do we know that? Well, OK, the ideal generated by x is properly contained in the ideal generated by 2 and x, which is properly contained in Z bracket x. So by the definition of what it means to be maximal, here's an ideal that contains our ideal generated by x and isn't the whole ring. So it's not a maximal ideal. But you can also check it with this proposition. We've seen that Z bracket x modulo the ideal generated by x is isomorphic to Z. And Z is not a field. Let's give a different type of example. Let's say R is the ring of all functions f from the closed interval from 0 to 1 to the real numbers r. If we fix some particular element of the closed interval a, we saw earlier that this evaluation at a map, which takes a function f to its evaluation f of a, is a ring homomorphism. So let's let MA be the kernel of that ring homomorphism. So that's some ideal of this ring of functions. Is it maximal? Well, what else is true about this evaluation function? It's surjective. It's a surjective ring homomorphism. So we apply the first isomorphism theorem for rings and see that R mod this ideal is isomorphic to the real numbers R. And this is a field. So that means that this ideal MA is a maximal ideal. So this proposition is a really, really useful way to check whether an ideal in a commutative ring with unity is a maximal ideal.